Hello, my name is Kate Seaver, and I'm one of three group members from Group 3 reporting our rotating wing presentation. Starting off with our introduction on what is a Samara seed. A Samara seed is known as a helicopter seed because it is an auto-rotating device. This means that asymmetric airflow causes the seed to rotate around its own axis. The wing itself is a flat and thin curved membrane with an increased surface area. Later in our data, you'll see that this increased surface area actually aids in lift generation. Another important thing about Samara seeds is that their drag is balanced by lift. So that allows these seeds to travel long distances over long periods of time. A brief overview on autorotation. This is when aerodynamic forces produce lift over engine power. So autorotation occurs when a difference in air pressure is created above and below rotor blades, like on a helicopter, when these blades are pitched at specific angles of attack. So as the autorotating device descends in the air itself will drive the blades to produce lift, and your descent time is controlled by adjusting the pitch of these blades. Next, I'm going to talk about the methods we used for our experiment. We started by collecting the seed area, mass, radius, chord length, span, and projected area values for each of our 6 seeds. Then we dropped a seed from about 3.28 meters in stable air conditions for a total of 5 trials. We recorded the descent time for each trial and then averaged those. After that, we repeated that process for the remaining 5 seeds, and then we were able to substitute all of that data into our 6 pi terms, which I'll talk about next, and our one-dimensionless time parameter. Then we plotted each pi term against that dimensionless time parameter to conclude which variables actually affected the descent time of the seed. A large portion of our experiment was based on Buckingham pi, because this is how we evaluate which variables actually affected the descent time. For our experiment, we used air density, velocity, and diameter to be our repeating variables, and our non-repeating variables were chord length, gravity, area, mass, span, and viscosity. This ended with these 6 pi terms, as well as that 7th dimensionless time parameter. The procedure is pretty simple. You're just going to start by determining the dimensional formula for each variable. We have these listed in this table with all of our variables and the corresponding formula. Here, M stands for your mass units, L is your length units, and T are your time units. From here, you can proceed with the calculation, starting out with that basic pi equation, substituting each variable with its dimensional formula, and then using those exponents to figure out where the variables are placed in that final pi term. For example, m is raised to the power a and 1, which would result in the equation a plus 1 equals 0. From there, you see that a equals -1, meaning that the corresponding variable air density will be placed in the denominator raised to the first power.
My name is Sid Alston. I'll be going over the hypothesis part of our project. Our hypothesis kind of consisted of one main point with kind of 2 or 3 subpoints. That main point being that the flight and descent time of a Samara seed will be primarily influenced by its size, shape, and relative airspeed. So an increase in size and mass will result in an extended flight time is what we hypothesize. And in higher velocity conditions, the flight time will also increase compared to calm conditions with lower relative velocity conditions and relative airspeed conditions. Now I'll go over our control volume analysis using conservation of momentum equation. So this here is our control volume. As you can see, the boundary layer is pretty far out from the seed. The reason we did this was to eliminate the disturbances to the airflow by the seed at the boundary line. So essentially, the air that's traveling up towards the seed, it's undisturbed that distance below the seed, and then above the seed, I try to give it enough space to where the disturbance of the air by the seed is gone by the time it gets to that boundary line. So essentially, that way you have the same momentum flowing in and out of this boundary, and that will cancel that second term on the left um, for your momentum equation. And then the other term on the left side of the equation will cancel out due to the steady flow of momentum in and out of our control volume. And so then you're left with the two terms on the right once you say that you're assuming no viscous forces. So these two terms on the right can be equated to the drag force and the force of gravity. So the drag force will be equal to the pressure forces acting on the CV, because the pressure forces are what cause that drag force. So the differences in pressures above and below the seed is what cause that drag force on that seed, and that drag force is acting opposite to the gravity force, so which means that it's the lift force. So that drag force will be equal to the pressure forces in this CV, and then gravity is a body force, and so we set that equal to the triple integral in our momentum equation. And then you once making the assumption, the correct assumption that a seed in auto rotation is with stable relative airspeed conditions, it's traveling at a constant speed down towards the ground. And for it to be traveling at a constant speed, the lift force and force of gravity must be equal. So the force of gravity is equal to the mass times the gravity. And then the drag equation used is the equation for an object traveling through air at a steady speed. So this drag force equation, 1/2 rho CD AV squared, is the equation of drag force for an object traveling through air or fluid at a constant speed. You set those equal to each other and you isolate V, and so you get that equation. But now you can plug that into the simple equation of time being equal to the height over the velocity. So you plug that in, so you have height over the square root of 2mg over rho CDA. Now, in the literature review, we found that the drag, the coefficient of drag for a lot of these seeds, if not all of them, is right around 6. So plugging in 6 and plugging in the area of each seed, the mass of each seed, and then using the density of air, the force of gravity, and then our height for the experiments, you can get theoretical times for each seed falling using its specific dimensions.
My name is Hollis Prosser, and I'm going to be going over the experimental data and conclusions. So to start with, we organized all our measurements from the experiment into a table, including our independent variables, which are seed area and mass, and then our dependent variables, descent time and velocity. And then we used a number of constants to convert those into dimensionless parameters, which we then compared with our normalized descent time to find trends and how those parameters affect the descent time of the seed. So our first graph is our dimensionless time versus dimensionless size. And here it appears that a larger size parameter roughly corresponds to a faster descent, but there's not a clear trend as to at what rate that happens. Seeds with size parameters of 138.42 and 138.18 had our shortest descent times at about 3.7 and 3.03 seconds. On the other hand, the slowest times were observed for the smaller size parameter of about 119. In figure 3, we see the effects of Froude number on descent time, and it shows a clearly positive slope. So as Froude number increases, so does descent time. And this suggests that seeds with a higher initial velocity and greater lift to drag ratios will experience longer descent times. So essentially the inertial forces outweigh the gravitational forces and extend that descent time. The figure 4 shows dimensionless time versus Reynolds number. And here the trend is reversed. So as Reynolds number increases, we see a decrease in descent time. So a seed with a Reynolds number of 3,850 descended in 3.03 seconds, but one with a lower Reynolds number of 2,940 took 4.43. And this would make sense as a higher Reynolds number is equated to a greater velocity, which would decrease the time needed for the seed to reach the ground. Figures 5 through 7 explore the different dimensions and areas of the seed's airfoil surface, and then how they compare to the dimensionless time. And it appears that the most effective is going to be the span of the seed compared to its diameter, as it shows that as that value increases, so too does the time, while the other two, seed area and the chord length, seem to have no real discernible effect. One noteworthy observation is that all of our theoretical times are longer than the experimental times. This is likely due to the fact that in practice, the seeds experienced free fall before they began auto-rotating, and this was not accounted for in the theoretical calculations, which would mean that their actual descent time under auto-rotation is shorter than the descent time than the height they were dropped from. Thanks. Some sources of error we might have encountered are precision in our timing. We were using a recording of a stopwatch and the seed hitting the ground, and there's some inbuilt delay in the video and how we might have perceived the timing. Visual delay from our reaction time seeing the seed hitting the ground and the stopwatch. And then our measurement precision, because we're only going to a couple of decimal places in seconds and we're doing fractions of millimeters and inches to measure. So there's definitely some more measurement that could have been done. Our revised hypothesis following the experiment is that the flight and descent time of a Samara seed will be primarily influenced by its size and shape and its inertial relationships, and that an increase in the size and mass will result in an extended flight time. The descent time of the seed will decrease as the number increases. So essentially, the larger the seed, the longer its flight time, and inversely, the faster it falls, the shorter the flight time. So wing area, chord length, and model size have negligible effect. But as the span diameter ratio increases, so too does the descent time. And as the Freud and Reynolds numbers both increase, Freud's number will increase the descent time, and Reynolds' number will decrease the descent time.